Hey everyone, it's Adam again, and we're going to continue on with our talk of epi and biostats. Our next lecture, which is going to be on confidence intervals. So we're going to do a little bit more kind of in-depth looks in things like how we can define and apply confidence intervals to a proportion. And we're going to look at some information about survival data and how we can kind of graph that and apply confidence intervals to that information. So first off, we're going to look at the confidence interval of a proportion. So we know that our confidence intervals are useful for helping us to generalize information. Basically, what we are using confidence intervals with our our sample data, which again we know to be true, assuming we measured everything correctly, and we're going to take that information and then try to apply that out to make more kind of general conclusions about the population that we are interested in. And so you're going to see, especially when you're looking at results that can come out as a proportion or a fraction, they'll have a range around them, and so that range is going to be that confidence interval, both upper and lower limits there, as we'll see. And again, when we're trying to compare this back to the true population mean, we want to have the greatest assurance that this is accurate, and so the goal is to have the smallest confidence interval possible. This way you can say that, hey, I'm 95% sure that the true value or the true mean of the population is going to be within this very narrow set of values, as opposed to being something much more wide, which would have a wider range. You like to be as exact as you possibly can. And again, it's done by pretty complex math, and again, not going to be done by us in a lot of cases. A lot of this gets kind of automatically done with statistics software. So many journals are going to require the use of confidence intervals, and they oftentimes will get reported, as we'll see when we do our journal clubs. And so we'll be able to identify those and be able to interpret them with pretty good results, as you'll see as you get more practice with it. Again, this is going to provide more information than strictly what a p-value would tell us, and you'll see that when we talk more about p-values a little bit later on. And so basically how you would phrase the use of confidence intervals is something like, hey, we are 99% confident that the true value of a parameter is in our confidence interval, right? So that would be very, very exact, that you are very, very sure that within this given range, the true value lies within this. More often than not, you're going to find the use of 95% confidence intervals. So for instance, if you're looking at a sample and you're finding that mean and trying to compare it back to the population mean, which again, we can't know what the population mean or average would be, but we can take our sample and say, hey, we are 95% confident, or there's a 95% chance that that this confidence interval is going to contain the actual true population value. So again, your confidence interval size, or the width, is going to depend on several things, which we already looked at, including the sample size. Typically, the larger the sample size, the smaller our confidence interval is going to be, because we're getting closer to that population value, that n, as it gets larger, and we can be more reasonably sure that our sample is kind of an accurate representation of that population. And so we can say that, hey, larger the sample size, the smaller our confidence interval is going to become. And again, we know that based on the math that we saw previously in the last lecture. The size of the standard deviation, the more variation there is in the data about the mean, the larger that standard deviation, the larger the confidence interval becomes, because that means that the mean is going to be less certain as we have more variability in the data there. And then the degree of confidence that you want is going to be important to determine this. So if you were to have, say, a sample and you were looking at trying to compare it back to a population, I can say, well, if I want to be not very certain, then I can be pretty exact with that, because say I'm 50% certain that the true population value is X. That's a 50% shot that I'm right and then I'm wrong, so I don't really have to be that exact with it. However, on the other hand, when you are looking at becoming much more confident about that, so if I want to have 95% confidence interval or 90% confidence interval, you're going to see that you need to include a larger value for that confidence interval, so that way you can be sure that you're actually capturing the actual population value, because otherwise you're going to be more likely to make a mistake. So the more certain you are in saying that, hey, the value is 10, I may be wrong, I may be right, so it's hard to be really that exact. But if I can say, hey, I'm 95% confident that the true value is somewhere between, say, 8.5 and say 11.5. As I widen that out, I'm able to be more certain that the true value lies within that range. Okay. As I drop my confidence interval, I can narrow down or as I drop how confident I want to be, I can narrow that confidence interval. But the more precise I want to be, if I want to be 99% certain, the CI would have to be larger in order to encapsulate all those values, which the true value could be. So just to give you an example of this, one thing we'll look at is going to be deaths of premature babies. And so neonatal mortality rate is a very important thing to look at. Oftentimes it's used as a surrogate for how good healthcare is in a society, especially with prenatal care and things like that. But in this data from 1993, they were looking at the survival of these premature infants, so those that were born earlier than what you would normally expect for a term infant. So this was a retrospective study, meaning that it was information that they were collecting after it had already occurred. And so they're looking backwards in time at these babies that were born between, say, 22 and 25 weeks gestation at Johns Hopkins Hospital. And this is over a 3-year period. And what they found was, of the 29 infants that were born at 22 weeks, none of those survived to the 6-month time frame. Of the 39 infants that were born at 25 weeks gestation, 31 survived at least 6 months. Okay, and so when they represented this data, they were able to basically they said this without any kind of confidence intervals at the time. So looking at this information, you want to be able to kind of extrapolate this back and hopefully apply it to a larger population of premature infants. So for instance, if you had, say, a worried mother who is, approaching either say 22 or 25 weeks gestation, and she's like, well, what would my baby's chances be if they were born right today? And so those kind of questions, you have to be able to take this kind of sample information and try to apply it back to a population. So if you were to look at this, you were to say, hey, looking at the data that we see here, you could say that, okay, well, if they're born at 22 weeks in this sample that we had, 0% of those babies survived, okay, to 6 months. Does that mean that every single baby born at 22 weeks is going to not be able to make it to 6 months? You can't really say that. We need to have a confidence interval that can tell us what the range is to see, to have some confidence to say that, well, this isn't going to be the case. This is not absolute. But when we generalize this back to the population, what do we think is kind of the range in which we would expect these 22-month or 22-week infants to be surviving at? It's a little bit more kind of a better representative example here if you're looking at those that were born at the 25 weeks. So 31 out of 39, or roughly 79.5% of those babies survived to 6 months. You can't say with a 100% certainty that every baby born in the U.S. to 25 weeks gestation, 79.5% of them are going to survive to 6 months. You can't say that because you're being too certain there, and we can never know what the actual population would be. The actual population values, that survival rate. So we need to have a confidence interval that says, hey, we are 95% sure that it's going to be between, say, 72% and say 83%. That way we can say that, hey, 95% of the time we're sure that the actual population value is going to be within this range. And we'll see what that looks like in a second. So when you're looking at this, when they calculated it out, they said that, hey, the infants born at 22 weeks, the confidence interval range anywhere between 0 to 11.9%. Obviously, you can't have a negative percentage there in those cases. You can't, I don't know what that would actually, maybe like a zombie infant or something like that, but that would not be really applicable to this case. So 0 is kind of your lower border there. On the other hand, though, looking at the infants born at 25 weeks, they did a confidence interval range, and they said, hey, this is 64% to 91%. Basically, what they're saying is that if you were to take this sample data and apply it back to the population, they are 95% sure that a baby born at 25 weeks would have anywhere between a 64 to a 91% chance of survival at 6 months. So again, if you were to look back at your, go back to your patient who's really worried about whether or not their baby would survive if it was born early, and you say, hey, just to let you know, your baby may be anywhere between 2/3 to 90% chance that they're going to survive. That's pretty wide. I don't think many patients would feel very comfortable with those kind of odds, and they would want to become more certain about that. And so what we saw is that one of the ways that you can do to narrow up this confidence interval be something like increasing the number of observations you have, or increasing the N. So maybe if you had more infants to look at, you'd have a better idea of what the actual population value would be as far as 25-week gestation infants survival to 6 months. Maybe you can narrow that down, so maybe it'd be something like 70 to 90% or something like that. And so look at this range, and so the range is very important, and usually you want to have this be as narrow as possible, so that way you can be very, very sure that the values you're finding in the sample is very, very close to what the actual population value is going to be. Okay. So another good example of how we can apply these confidence intervals back into approximating what a sample might mean for the population as far as its true value or true averages. Let's say, for instance, we polled 100 random people before an election. So say we're trying to finally decide which is better, pie versus cake. And so 33 people of that 100 said pie is the thing that they're going to vote for. Okay, we all know them to be wrong, but that's okay. Those 33 said, hey, we're going to do pie. And so can you extrapolate that information to say that if you went ahead and did the whole U.S. population, for instance, if you went ahead and they voted for pie versus cake, would 33% of people vote for pie? You can't necessarily extrapolate that and say with 100% certainty that that would be the case, right? We're never going to be 100% certain on any of this anyway. But a couple things you have to consider is, one, is your sample really representative of the population of voters? So for instance, if I only polled from one very small area, say of Florida, say for instance I went to the Panhandle and polled those people out of Pensacola, is that going to be representative of the same people, say, that were voting in Orlando or that are voting in California? Okay, and so we can see what we call a sampling error here, where you may have a smaller or a larger fraction of people voting for a particular candidate than with the overall population. So say for instance, you're polling from certain socioeconomic status groups, or if you were polling in certain parts of the U.S., they may not be representative of the whole population in those cases, and so that would increase some bias in the information that you're getting here, and make that information that you're generalizing back to your population less accurate. So here, if we were to use that the 100 people that we polled, and we had that 33 out of 100 say, hey, they want to vote for pie, basically we can come up with a confidence interval. And so we can look at this, and so we would calculate a confidence interval that would extend from 0.24 to 0.42, meaning that if you were to have this extrapolated back, so say whatever population you're interested in, so let's say we're polling people in Florida who are going to vote pie versus cake. Basically, you could say that we are 95% sure, or 95% confident that if we were to have this vote today, that we would either have 24% of people voting for pie, anywhere between 24% to 42%. Okay, and so that way, again, it's still a fairly wide range there. And again, in order to become more confident, you could do things like either decrease the amount of variability in what people are voting for. This is less likely to be a problem when you're dealing with kind of a dichotomous variable, kind of like that. But you could also increase your sample size. So if I was polling 1,000 people, if I was polling 10,000 people, that would be able to shrink my confidence interval, so I could be much more confident because that group of people is more representative of the whole population rather than just looking at 100 people. So one of the big assumptions you have to make when looking and evaluating these confidence intervals is that the sample you're looking at is representative or random sample of the population, right? So we mentioned some of that bias that can be included when not really capturing a representative sample of your population. As I mentioned, if you were interested in all people with HIV, if that was your population that you're trying to make some inferences about, and you only captured, say, 20 to 40-year-old people were showing up in a university clinic, you would end up missing a lot of people out of that population, say older patients, younger patients, homeless patients, things like that. And so you need to make sure that you try to eliminate that bias, or at least the authors of a study have eliminated that bias by at least being pretty transparent about that sort of things, or at least listing as a limitation of their study. Looking back at the examples we were talking about, if you were to look at that baby example, if for instance you were somehow selecting babies that were going to be sicker, that would skew your data one way versus the other. So say for instance you're only looking at mothers who had no prenatal care, those are more likely to be sicker babies and less likely to have survived to 6 months. That would skew your data towards seeing higher mortality and may not be representative of all premature infants. Okay. Another good example would be if you were polling people about say a presidential race, and the actual sampling was not random. So for instance, in 1936, looking at the Roosevelt-Landon presidential election, basically what they were doing at the time was they were using phone books and auto registrations to poll people to see who they thought was going to win. Well, at that time, who were people that owned phones and who were people that owned cars? Usually people that were in a higher socioeconomic status, people who had money, and so they may not have been representative of all people who were voting. So if you weren't really capturing people who did not have phones or people who did not own cars, then you really missed out on the whole population, and you can't say that this sample is going to be representative of the whole population of everyone voting for president. The other thing you need to assume here is that we're going to have independent observations. So basically, we said that 95% confidence interval is only valid when all subjects are going to be independent from one another. This could be violated, for instance, if you were looking at the baby example, if you had twins. For instance, they could have similar genetic conditions or similar environmental factors which may have affected survival. If a mom had twins and was using drugs during, illicit drugs during the pregnancy, or if they shared a genetic anomaly that were predisposing them to higher mortality, that would skew your data as well, right? And so we need these observations to be independent from one another. So no siblings siblings are often one of those things you may exclude in studies like that. Another thing you might see with the voting examples, if you were to vote, if you were to poll husband and wife, you may find that some people are more likely to, agree to whatever their spouse. I'm sure if my wife said she was going to vote for pie, I would obviously just go along with it because I just don't want the trouble. I just don't want to cause any arguments, right? And so the other thing would be, if you're only, say, polling people, say half the subjects were from one city and the other half from another, you can see some skews there that would lead to having some bias in your information. Again, you are hoping that the data you're looking at is going to be accurate. Again, so you need to make sure that everything is being measured the same way. I mentioned that temperature example. If you had someone who's doing rectal thermometer checks versus oral, that would obviously skew your temperatures one way versus the other. For things like mortality, it's pretty easy since death is kind of a pretty it's kind of a black and white kind of thing where it's like either you're dead or you're not. On the other hand, though, if you were to look at the polling example, this can be really, really important because if you're using things like leading questions or if you're using intimidation or things like that, you may skew what people might actually answer. So, for instance, you're like, well, only a fool would ever say cake is better than pie, which, you're not a fool, are you? Things like that would be kind of a bad way to ask those questions. So, especially when you're evaluating literature that is looking at things like surveys, it's really, really important to look at what types of questions are they asking and is that skewing their data one way or the other, because that can lead to some erroneous conclusions. So when you're evaluating the literature and someone says, hey, we are 95% confident that the true population mean falls somewhere within this range. That means that 5% of the time they're going to be wrong, right? Because this is kind of they're right or they're wrong. And so you can find that when you're 95% sure, 5% of the time it's not going to be true. And so, and again, you think, well, don't we always want to be 100% confident? You can never really be 100% confident because of the fact that you never really know what the true population value is going to be. However, one of the things you can see, especially in this graph, it's very kind of representative of this, is the fact that if you were to rerun the same experiment 20 times, you would find that 19 times out of 20, you should be correct, right? 95% of the time, you should be right. But 5% of the time, you're going to be wrong. So in this experiment, what they did was they simulated, basically had a bucket, 25% of the balls in the bucket were red, the rest were black. And so they were drawing balls at random to determine what percentage of those were going to be red. And you can see that in most of the experiments, you can see the horizontal line is going to be the mean, and then you can see the confidence interval. And so they say, okay, well, based on all of these, even though the mean itself that they calculated from the sample was not 25%, the confidence interval on either way actually is going to include that 25%. So they can say, I am, 95% sure that the actual proportion of red balls in this bucket ranges anywhere between, say, 35 to 15%. Okay, that still includes that 25% that was actually there to begin with, right? So that's the actual population average that we already know because we set up this experiment. But if you note, there's just one experiment here where they pulled a higher proportion of red balls, it looks like, and so they can see that, hey, it looks like over 50% of the balls in here are red. We're 95% sure that the true value or the true proportion of red balls in this bucket is somewhere in here. And notice it doesn't even include what the actual population value is. And so that's one of those things what we're evaluating when we're looking at the literature is they're saying we're 95% sure the true value lies within this range. And again, just sometimes they're going to be wrong. And that's one of those things we just have to take as a caveat. And that's why it's really important that we have repeat and validation of experiments because that way you can make sure that the results are actually correct, right? You need to make sure that the same thing is going to happen very consistently and you're not going to have erroneous results like this being reported as truth. And that's one of the big problems you're going to run into with medical literature is the fact that no one likes to to publish negative results, and then no one likes to publish results that have already been shown before. Again, they want to see new stuff, they want to see novel things, and so if you're trying to say, hey, we just reproduced what this other guy did and saw the same results, no one really cares, right? They're looking for new stuff because they want to get people to read the articles, they want people to buy the journal, etc. And so this is one of those important caveats to remember when evaluating the literature. So again, you need to make sure that the event that you're tallying is actually the thing that you're really concerned with. So for instance, with like infant mortality, that's exactly what you're looking for, because you're looking to see, how is the prenatal healthcare being done? How is this kind of correlate back to healthcare in general for a society? And infant healthcare can be, or infant mortality can be one of the things you look at. Another thing, if you're looking at the election example, so again, if the poll results were assessed on a particular date and they were to be extrapolated to election results in the future, well, what if something happens? There's some big scandal where suddenly cake is found to be made with asbestos. Now all of a sudden people's ideas about cake versus pie are going to change. Now all of a sudden they don't want to vote the same way they did before. So sometimes there's a time frame issue there to where you want to make sure that those results are going to be still applicable there. Okay. And so, again, you can only extrapolate and make additional assumptions based on what people say the way they're going to vote. So, for instance, in 1948, the presidential election, Dewey versus Truman, basically they were seeing that the polling started in early September while the election was happening in November, and people ended up changing their minds for whatever reason. And so there's this kind of famous paper that said Dewey defeats Truman. A lot of that was based on those early polling results that were not reflective of how people truly voted. Okay. So looking at some of the lingo, so confidence interval versus confidence limits. Basically, the two ends of the confidence interval are called those limits. So the limits are basically the high and the low values there. And so the confidence interval itself is a range. It will extend between those limits. Estimate is going to be a special term that we have in statistics. Basically, it's going to be the result of some sort of defined calculation. And again, that value computed from your sample is only really an estimate of what we think is a true value in the population. We can't know the true population value, but we can at least have an estimate based on the sample that we are drawing from. Okay. And so then the confidence level, there's nothing really special about that 95%. It is simply something we've done for many, many years and decades. In some cases, you may see that being changed in certain articles. Sometimes they may be looking at a confidence interval of 99%. Okay, it just means that they are that much more sure that the true population value lies within that range. Looking here, you can see a good example of how the percent confident you want to be in your results and how that has a direct effect on your confidence interval. You notice here that when looking at the 90% confidence interval, notice how it's the most narrow out of the bunch. As I try to get more and more confident, because I'm saying more and more likelihood, with more likelihood that this is the absolute true value, I need to be able to extend this out, because otherwise I'm more likely to make a false report. I'm going to have a false positive result there, and so I need to be able to make sure that I can account for that by having a wider range, so I have a wider margin for error. Okay. So again, the higher the confidence, the more leeway I need to give myself, the bigger the range is going to be on that. Okay. This is a nice picture that will show you essentially what the effect that sample size is going to have on confidence interval. And so what you'll see, and we saw in the kind of the math done on the previous section, is that as you increase your sample size, because we're getting closer and closer to that true population number, essentially, you're going to find that the confidence interval is going to be shrinking as you go along with that, right? So that way we can see as we get a larger and larger number, we can be more certain that the actual population value lies within this range. If we're only dealing with, say, if I have a population of, say 1 million people, and I'm only sampling 10 out of that, I'm not going to be very sure about that. And so I need to have a very wide range to encapsulate exactly how far off I may be in my estimation of what the population value is. But as I get closer and closer to the whole entire population I'm interested in, that confidence interval is going to be shrinking pretty considerably. So again, usually a larger sample size is generally a good thing when you're looking at the medical literature. Sometimes you're not going to be able to get away with that. Sometimes a study of 30 people is all you can get based on certain factors. But obviously, a higher number here is going to be able to reduce our confidence interval. In general, you're going to find that confidence intervals tend to be roughly symmetrical around the mean of your sample, but in some cases you may find that it gets a little lopsided. So for this case here, you can't really go above 100%, so that would be kind of the upper limit of it, so that would cause it to be a little lopsided. Again, the mean is going to be this bar, or this line that goes through the middle here. On On the other hand, if you have a very small number of patients, or the farther and farther away you get from, say, 50%, you're going to find that it tends to get a little bit more lopsided. That's just kind of the nature of the beast when it comes to that. But again, generally, the more people you have, the closer to kind of the 50% mark you are, the more symmetrical it's going to be. Okay, next we're going to look at survival data. And again, if you go on a long enough time curve, everyone's mortality rate is going to be 100%. I hate to say it, but we're all going to bite the dust one day. So again, when you're looking at survival data, really the only outcome that you're interested in right there is death, and it can only happen once. Not a whole lot of people end up dying twice unless you're, say, James Bond or something. But basically, this gets displayed in graphs that will show the percentage of people who are still surviving as a function of time, because you typically want to see how long people are surviving for, and so you can look at these graphs that will do that as a function of time. And so we'll say the term survival curve, but it tends to be a little bit misleading, because basically what we're going to see is that you can plot time to any really well-timed or well-defined endpoint or event. It doesn't have to be survival necessarily you're looking at. You could look at something like births of people. Because you can have a well-defined point or event. Someone's born, or someone is diagnosed with HIV, something like that. So saying this is a survival curve only is misleading for that in that regard. But in general, when looking at this, you will see that it must be based on one-time event. It's not something that can recur. For instance, you wouldn't want to use a survival curve for something like contracting the flu, because people can get the flu several times in their lifetime, right? Versus something like HIV. Once you have it, you got it. Or once you're born, once you're dead, that's it. And so basically, you have to know the survival time for each subject, or at least when the data were censored. We'll talk about censored data here in just a few minutes. So, and sometimes you're looking at the censored data. Sometimes survival times are not going to be known. Sometimes you lose patient to follow-up. Sometimes they move away. You may not have all the data that you really need there. You'll find that many studies have kind of a rolling enrollment period, where basically they will be taking new patients into the study over a period of several years as they become available. Patients who enroll later, and they will not be followed as long because they are going to be closer to the end of the study period. So they don't get followed as many years as those who enrolled early. And then that could be one reason why I have some censored data. The other thing is just that loss to follow-up, or if they end up surviving past the end of the study period, that would be another reason. So we'll talk about what that censored data really means. So again, censor means basically trying to if you ever see someone who is a patient who's removed from the data and say, hey, we're going to censor this person because we don't want them to skew the data because they either died of an unrelated cause, say for instance you're looking at cancer survival and someone dies from a car wreck. Well, it probably wasn't attributed right to their cancer, so they probably would censor that kind of thing. Typically, you need to account for these, though. You can't just take someone out of the study and never report on that. You should really have literature that will say, hey, we had this many people in the study, we had to censor this many accounts because of these reasons, right? So this many people were lost to follow-up, this many people died of unrelated causes, whatever happens to be. They really need to be transparent about that sort of thing. And so when we're looking at this, sometimes people will do analyses where they'll look at all the data they have, and then sometimes they'll look at it minus the censored data in order to see if there's any kind of big discrepancies there in their results and their conclusions. But basically, the survival analysis is going to be taking into account how long each subject is known to have been alive and to follow the protocol of the study that you're in. Okay. And again, no information after the study period should be included, because once the study is done, that's it. You don't want to take any more information after that because it may not be valid based on the study. So for instance, if you're looking at some censored survival data here, let's say for instance we had several patients who were starting at several different dates between 1998 and 1999. You see the ending date here, and you'll see what happened to the patient. So for instance, you'll see some people had died. One person died in a car crash. That would be something that may be unrelated to what you're actually looking at. The study ended, so they're at the end of the study and they were still alive. And then someone that they moved, no longer on the protocol that the study had set forth, they might be censored as well. So we'll look at this, what this looks like on the graph in just a minute. So looking at this, we had 7 patients in the study. 3 of the patients ended up being censored, and then 1 of the censored patients ended up dying from an unrelated cause. So again, some studies you'll find will do kind of all-cause mortality, meaning they will include any type of death that occurred, whether it be unrelated or not. Even if a person killed themselves or they got mugged and got shot during that, they would include it anyway, even if it may not be really germane to what you're looking at. So in this case, though, it would be considered a censored observation, meaning they would take it out of their analyses, but they would at least report on it to show you that, hey, they did take into account all these patients. And so the patient who lived 3.67 years on the treatment, again, it was one of those things where it might be unknown how long they would have lived had they gone past the study period. But again, once they're at the end of the study, that's you can't really include any data after that. So here, looking at the data, you can see basically how long all the patients were in the study for, and you can see that they'll be assigned codes based on whether or not they're going to be included in the study or not. So ones that are ones are going to be included in the analysis, whereas the zeros will be ones that were censored. Basically, they would not show up on the survival curve. So before we get to the actual curve itself, there's several ways you can graph these survival tables. There's this actuarial method where you'll find that the x-axis is going to be divided up into regular intervals, and there's also what we call a Kaplan-Meier method. We'll call these more commonly known as Kaplan-Meier curves. And basically, this is the more common one we're going to use, but the survival time is going to be recalculated with each patient death. And again, unless it's a very large study, this is going to be the preferred method. Basically what it does is it calculates the fraction of patients who survived on a particular day, divide that number or divide the number alive at the end of the day by the number alive at the beginning of the day, and this will account for all censored patients. Oftentimes it's going to be done by the computer, and keep in mind that the 0 times the date that each patient entered the study. So basically every person is going to be considered to start at day 1 based on when they entered the study. Okay, and then you can expand for years based on the enrollment period. So sometimes you'll see some different analyses based on that. Okay, so when you're generating one of these Kaplan-Meier curves, essentially what you're going to do is include everyone at the very beginning of the study. Again, everyone, no matter what day they actually joined the study, this would be considered time point 0 for all of them. So again, at the very beginning of the study, 100% of those people would still be alive. Obviously, they would not admit anyone to the study if they're already dead. This kind of defeats the point. But you can see that there can be a confidence interval that is associated with all of these values as we go along. So for instance, if we start at the very beginning, it's all at 100% because everyone's still alive. The first event occurred when someone died at 1.39 years into the study. Here you're going to see that we still have 85.71% of patients still alive, and you can see the confidence interval is going to be there. So again, if you were to extrapolate this information back to the population you're concerned with, the population they're trying to look at in this study, they would see a pretty wide confidence interval for how many people would be still alive at roughly 1.4 years in. Okay. Next, the next event occurred at 3.67 years. You can see here now we have still 85.71. This is probably a point where someone was censored, right? So again, the values are going to still be the same here. Okay, so you can still include censored data because again, it's just an event that occurred, like maybe someone moved away, whatever happens to be. Then at 4.07 years is when again another person died. 4.76 again another person died. So the survival percentage is going down, and we're seeing a pretty wide confidence intervals here, as we'll see. And so again at the very end, this is our people that are getting censored out. So you see really no changes here, but again the confidence interval associated with that. So I'll show you what the curve looks like here in just a second. So several different ways you can plot this data. So for instance, if I were looking here, notice here we have percent survival is going to be on the y-axis. The years and our time frame in years is going to be on the x-axis here. Again, everyone starts at 100% because we have 100% of people still alive. You can notice here how we have an event occur, so someone died. So again, the percentage is going down, pretty wide confidence intervals. Next, you're going to have someone who gets censored. So sometimes I'll include that as being a dot or like a dash, as you'll see here. And then as people die off, and then you have some censored events that occur here as well. So again, as the percentage is going down, you can kind of see that, okay, well, how many people were basically alive, say, at 5 years? You can kind of look at this and say, okay, well roughly 5 years, 50% of the people were roughly left alive, essentially. So again, different ways you can kind of graph the same information. Sometimes I'll have these kind of shaded bars here, so you can kind of see a range of like, okay, well, looking at this, if I was at 5 years, what's the range of people I can expect to be alive if I were to extrapolate this back to a population? You can say anywhere between, say, like 70, 80%, all the way down to maybe something like 30%, based on these kind of bars. I can expect my patients, if they were to survive if they were to live up for 5 years, what are their chances of being alive at this point? So one of the ways we can kind of consolidate that information from those Kaplan-Meier survival curves is by using what we call the median survival. And so essentially this is a really good way to compare different treatments. So say for instance you were comparing cancer treatments and you wanted to compare one type of treatment regimen versus another and see how that affected survival for your patients. And so basically what you can do is get the median value, again, which again is that 50th percentile of a set of numbers, and see how long it takes until half of the subjects have died. Okay, so then when the horizontal line at 50% of the x-axis crosses the survival curve, And again, you can see that we'll see it in those curves. That this would be basically when you have the time it takes to get about 50% of people dead. Okay, the median survival time is going to be undefined when you have more than half of the subjects that are still alive at the end of the study. So you really need to have at least 50% of those people having died by the end of it. Not that you want your patients to die off, but again, that's one of those things you really need to have to be able to calculate a median survival. So. One of the things we'll look at, you may hear, especially with cancer treatment, though, is 5-year survival. This is kind of a arbitrary sort of time frame, more of a matter of tradition than anything else. But again, because they can then now compare different types of treatments to see, well, what was the number of people alive at the 5% mark for treatment A versus treatment B. So sometimes you'll hear that, and that's kind of what that's referring to as well. Again, it can still be used with those Kaplan-Meier curves. So some of the assumptions to make when we're looking at survival analysis is that one, it should be a random or representative sample. This is just the same as what we were talking about when we were looking at confidence intervals of a proportion. And again, these need to be independent subjects, okay? So for instance, you don't want to have siblings you're going to be looking at or people of the same family because they could have, say, genetic predispositions that lead them more likely to die or to live. Basically, we want to be able to keep everyone independent of one another that really have no influences on one another. Entry criteria should be consistent. So as people come in, and we'll talk about inclusion criteria a little bit later on, but basically everyone needs to be coming in with the same kind of criteria. Sometimes what you'll find is that things like diagnostic tools can actually affect survivability. So if, say, for instance, we have a new tool that comes out that allows you to detect certain types of cancers, say 10 years earlier than you would otherwise, that would obviously greatly improve survival because you could start treatment that much sooner. So you need to make sure that when you're evaluating things like that, that everyone is included in the study very consistently using the same sort of enrollment methodology. You also want the endpoint to be pretty consistently measured here. So again, do you want all deaths to count? Do you want this to be an all-cause mortality, or do you want subjects to be censored if they died of an unrelated cause? So if I was checking prostate cancer survival rates and someone died from a car wreck, do I include that or not? And the authors of the research should be very clear about that and very transparent. And if not, then that can create ambiguity and it can be very difficult to make any inferences from those results. And so again, it should be applied consistently throughout the study to all people. And then the starting time needs to be clearly defined. Again, so it should either be, say, from the first diagnosis or from the first hospital admission or whatever it happens to be. It's not usually good enough to use patient recollection of like, hey, when did you develop hypertension? Usually there needs to be some sort of documentation of this to make sure you don't have any kind of recall biases. We'll see that's going to be termed. Usually patients who die early, say like before they ever get a chance to receive treatment, should not be removed. You want to include all those patients in there because if you take patients out kind of unnecessarily, that can introduce bias and it may skew your results towards showing a difference when maybe really none existed in the first place. And then what we call intention to treat is the standard. So again, even if someone never even received treatment, if they were assigned to that group, they should still be able to be included in that group for the analyses. That way you don't have kind of unfair comparisons being made. Also, censoring unrelated to survival. So basically, survival analysis is only really valid when the reasons for censoring are unrelated to survival. So, for instance, if a patient drops out of the study because they're too sick, or say, for instance, they cured their cancer, or they didn't feel like treatment was working, all that could be related back to disease progression. And so, because of that, that can have they can bias your results one way versus the other. And so what they will sometimes do to try to account for this is they will do analyses with and without these censored patients, as I mentioned before. If you find kind of similar results before and after, then you can be kind of rest assured that those patients were not really skewing your data. But again, the idea is to have that intention to treat where you include all of those patients regardless. Otherwise, people can call into question your results and say, well, maybe you're introducing more bias than need what there should be. And then average survival shouldn't really change during the study. So for instance, it's really only meaningful of an assumption if you assume that the first few subjects came from the same population as the last few over that enrollment period. So it really shouldn't be any big changes over there. So for instance, if you have the nature of disease over the course of the study changes. So if you have kind of a rapidly evolving infectious disease where it develops resistance very quickly, and all of a sudden the survival that applied to patients early on in the study period may not really apply to them later on now. right? And also it's important that the treatment, including things like supportive care, does not change over the course of the study. So all of a sudden, if they introduce some sort of new method of therapy that was not accounted for, that may skew your survival results, again, one way or the other, and that could skew your data. Sometimes the question we hear is, why do they report median survival time rather than mean or average survival time? Basically, you can only really compute the mean survival time when you have no censored observations, and if the study is going to include, it's going to follow people for a long enough time so that everyone dies, right? Which could be a very long time in some cases. Rather than that, we can utilize our median survivals and be able to get that 50% mark. It's much easier to hit that. It's much more just feasible for the studies to do that. So again, once half of the subjects have died in that group, that's when we can get a good median survival, and it's pretty unambiguous at that point. Okay, so that does it for this section. If you have any questions, please let me know, and I'll see you for the next lecture.